Hey there, Math Moment Makers. It's Kyle here from MakeMathMoments.com. And today in our video, I want to talk about emerging mathematical behaviors in the math classroom through questioning. And I'll tell you a little bit about what got me thinking about this idea and or I guess inspired this idea. And then I'm going to share some ideas on how you might be able to implement this same this emergence of mathematical behaviors in your own classrooms. We'll point you to some resources that might help you with that. So stick around and we'll get going in just a second here. Now, when we're thinking about our math class and really what it is that we want students to take away from our math class, more and more I realize that what I want students to see and understand is this idea of like the big ideas of mathematics and then also how mathematics behaves, in particular when they're working with numbers and operations. And what got me thinking about this video was actually from an email that a colleague had sent me recently. Here, let me bring it up on the screen. Of course, I'm going to hide the name for privacy reasons. But basically, this is a fantastic educator who noticed a very thoughtful math student who wanted to know why 7 plus 3 is the same as 3 plus 7. The idea that this educator brings up, this idea of taking a mathematical mat and basically placing 7 cubes and 3 cubes on one side and having the student rotate the mat around is really an awesome idea. You can sort of see it here, that I can see 7 plus 3. And if I just flip it around, we note that none of the cubes have actually been taken away or added. And therefore, that quantity, that total quantity of 10 cubes is maintained. And this idea actually does have a name. The educator was asking, is there a name for this mathematical behavior? And some people would know it as the commutative property, the idea that 3 plus 7 is the same as 7 plus 3. If we flip this around, we could say that it is the same. It is equivalent, 7 plus 3. And this commutative property is a mathematical behavior that we want students to pick up on as we engage in mathematics. But here's the thing, is that this wonderful student that this educator had noticed, this student was curious about why that was true. This student essentially on their own realized, or at least through the email I'm assuming realized on their own, that there's something going on here, that they're noticing that, wow, when the addends are switched, that the sum is the same, it's equivalent. Now, maybe the student's not able to articulate it using the same language, but the reality is this student is curious about why this is true and is seeking for understanding, is seeking to reason and prove this idea. Now, here's the problem though. In our math classrooms, there's so many things going on, and oftentimes, we just hope students will pick up on the patterns on their own, and some students will. But many students will not. So the question then becomes is how do we get more students thinking like this particular student? And what we want to do is we want to design our math lessons or our math spaces in a way that allow for students to sort of bump into this learning. And we can do that through questioning. So some of the things we're asking students to engage with, in a kindergarten class, maybe it's a play-based kindergarten class like we use here in Ontario, you set up provocation spaces, you set up areas, and if we're intentional about the questions we're asking students as they interact in these spaces, we can help them to emerge some of these behaviors. But noticing and naming these behaviors is important on our end. So today, I want to talk a little bit about that. So secondly, I'm wondering if you pause for a second, you think about this particular student And think about what we could do with this student. We could talk about the commutative property. Depending on the age of the student, is it appropriate for that language to come out? That's for you to decide. I would argue that many students are able to handle the language. I'm not expecting that they use the language, but I can notice and name it, and I can use that language, and they might call it something else. Maybe they call it like the swapping rule or something like that, the switcheroo, whatever works for them. But for them to get this behavior that, wow, these add-ins can actually commute, right? They can actually commute. With older students, I talk about commuting to and from work, this idea that I can switch places. So this idea is really important. But then we don't want to end it there. We don't want them to just, now they've answered the question. Where else could we go with this? So think about what is a prompt that you might consider asking this student after they've seen this take place. We could part ways and the learning for this idea or this concept may be done, or we could ask them another question. Now, there are many different questions you might consider asking them. Maybe one of them might be, does it work for all numbers, or is it just 7 and 3 that this works for, right? Or is it only single digit numbers, right? Numbers between 0 and 9 where this works for. Or another question might be like, is the same true for subtraction? And how could you show that? And you think about that question, that can open a great can of worms, bringing us into this idea of integers and the zero principle. So there's all kinds of other behaviors that we can explore in our math classrooms. But again, we have to be intentional on bringing them to light. So what I want to do is I actually want to talk about another behavior. So we talked a little bit about addition, this commutative property. I mentioned how you might use your questioning to extend to subtraction. Is this true for subtraction? I don't want to be the one telling the students. I want them to land on this idea that, oh, that is not true for subtraction. It does not always work. Are there times when it does work? I wonder if they could find other values of subtrahend and minuend that would work where they swap. Like, when does that work for subtraction, if ever? There's great questions that can be had. Now, if we extend this thinking here, I want to introduce one more behavior before sharing where we might go and emerge some other behaviors and some resources that are designed in order to emerge these behaviors. I'm going to clear the board here, and I'm going to bring an array out here, and I'm going to talk about this, and we're going to look at this as, I'll bring it over to the side here, and I'm sure you can see this. Students may or may not, depending on where they are in their learning. But over here, we can see that this is actually like a 3 by 4 array. And the question I might have for them is how many squares? And you might have some students that are counting 1 by 1. You might have some students that skip count by 3s, 3, 6, 9, 12, or maybe by 4s, 4, 8, 12. Either way, they come up with a product of 12. This idea of 3 times 4, or 3 groups of 4, is equal to 12, and that's great. We can use and we can emerge this idea of the commutative property here as well by essentially taking the same idea, once again, and we can commute. So we can have students exploring the commutative property when it comes to multiplication. So if we go here and we say, well, there's that same 3 by 4, like what happens if we kind of think of it a little differently and we say, what about 4 groups of 3? Is that going to be the same? And most students will come to the realization that yes, it is the same. And then the question could be, does it look different? Some students would just say, well, I'm just looking at 3 groups of 4 this way. I say there's 3 groups of 4. I see them this way. And over here, 4 groups of 3, I see them this way. And I can see that here as well. Other students might say, well, actually, if we do this, like what if the groups are always, along the side here? If we always said, well, I always like looking at my groups and rows, and then we see how many per rows. This is 4 per row or per group. we can do the same thing over here, use the commutative property in order to see, and I'm just going to get myself off the screen here, in order to see that 4 groups of 3 is also equal to 12, that commutative property. Now, we can stop there, of course, but actually, like, I wonder if we were to extend this to some other properties here. So I'm going to, clear my board here, and I'm going to talk a little bit about this right here. We have our 3 groups of 4, which we see up on the screen right now. But also, there's another property that we can leverage. Like if I take this and I actually partition this array into multiple arrays, I could take this, what was 3 groups of 4, and I can make it look a little bit different. I can do this in a variety of ways, but one such way I could do this is I might do this and say, well, like, okay, so this is 3 groups of 4, okay? And actually, well, this is 3 groups of 4 as well. Okay, there they are. But what if I was to, just like break this array right down the middle, and I was to look at it this way? Like I could still call it 3 groups of 4. Like I can fundamentally see the 3 groups of 4 here. There they are, 1, 2, 3. But I can maybe represent it a different way. Like I might be able to argue that, you know what? This is actually 3 groups of 2 plus another 3 groups of 2. And what we've actually done is we've actually leveraged this idea of partial products. Like we've actually taken this and we've said, you know what if we were to break the 4 down into 2 plus 2, and we had 3 groups of 2 plus 2. There's one group of 2 plus 2. There's a second group of 2 plus 2. A third group of 2 plus 2. That is the same as 3 groups of 2 plus another 3 groups of 2. And this is called the distributive property. And this is another behavior in mathematics that we can emerge just through playing with numbers. And there's something else, like I can also call this something else. Like some people might say, well, what if you were to just say, like, what you have is 3 times 3 groups of 2, and you've actually doubled it. Like I can actually see it's like there's like 1 group of 3 groups of 2, and then there's 2 groups of 3 groups of 2. So I could actually say that, it's also 2 groups of 3 groups of 2. And what we've done, if we're thinking of it this way, is like we've actually leveraged a couple different properties here. We've actually leveraged, in this particular case, we're leveraging not only the commutative property, but also the associative property, where we basically, like, we've taken this and we've decomposed it into 2 plus 2 in this particular case for our distributive property. But here we've also looked at this and we've said, I can actually like take this apart, and I can like reassociate it and kind of move it into another place. So we have like multiple properties going on here, and these behaviors of mathematics are going on all around us in our classroom. But unfortunately, unless we're explicitly giving students the opportunity through questioning to explore them, oftentimes what we do is we give them dry definitions. We give them the definition of the commutative property, or we give them the definition of the associative property, or we give them a definition of the distributive property, when we could have them noticing and naming these properties through the doing of mathematics. Now, some people might be sitting there and saying, okay, it's easy for you to say you like playing with math all the time, which I will give you that. I do really enjoy hanging out and playing with mathematics. However, there are ways and there's resources out there that you can leverage in order to engage in this learning as well. So one of the ways that we can do this is by heading to our Make Math Moments website and hitting on the tasks button up here. And this tasks button will bring you to problem-based units just like this one here. This one's called the Olympics unit. And this Olympics unit begins with just a notice and wonder, as do many of our prompts. We like to get students situated with the context. We like to get them talking, and we also like to get them estimating. And day one, we're talking about archery. This is one of the events in the Olympics. And, you know, they see some arrows hitting the board, or at least that's probably what students will notice here. And we ask them, what do they notice and what do they wonder? And on this day, this task emerges to students making estimates about how well this particular athlete scored in the 12 phases of this particular event at the Olympics. And then it extends to giving them a small chunk, a small sample of data in order to start emerging the idea of measures of central tendency, mean, median, and mode. And, you know, the part that I really want to show you is some of the behaviors that we try to emerge throughout this unit. I'm not going to talk about all of them, but there's, you know, this big idea that we want students to pull at, which is this idea that the average or the mean is the great equalizer. And I think one of the best ways we can see that, I'm going to just skip over day one here and go right to day two's math talk. We have a math talk. It's a visual math talk. And students are watching, you know, a basketball game taking place essentially here. They're seeing the ball go through the hoop. We're getting some points. And each game we're sort of tallying here. And the teacher can then give some more context and say that, you know, this is a player on the team. And in the first game, they scored 12 points. In the second game, 13 points. They go through this process and they see all 5 games are shared with the students. And by this point, because day one was all about emerging mean, median, and mode, and naturally using this central number that students get to select based on what they believe seems reasonable for their estimates, we can then land on, all right, let's actually calculate the mean, median, and mode for the data set. And let's go further and actually push students to really try to figure out what would be the best measure of central tendency for this particular player. And when we look here, you'll notice like right away, some students might realize, well, there's actually no repeating numbers. So the mode might not be the best bet. But for the median and the mean, we might actually want to look at both to try to see, is there, you know, like, how's the range in values? How, you know, where is that average? Where does it land? And what might be most appropriate? And as students share their strategies, we also have some visuals. And this is the one behavior that I wanted to share from today. So after students are given an opportunity to think, we'd pause the video and let them think. And then they would share out to the group, and then we would want to help them, especially in this particular case, I want them to see this idea of the mean. So here we have our 5 games shared, you know, 12 points in the first game, 13 in the second, 18 in the third, 15 in the fourth, and 17 in the fifth. And what we want students to be able to do is kind of like by visualizing this data, like what makes most sense? Do we want to find the median, like that middle value, or are we good with finding the mean? And what does it actually mean in order to find the mean or the average of the data set? And through this learning, we want them to see this behavior that, you know, I know how I learned to average numbers. I would add up all the numbers and then I would divide them by the number of numbers, right? Like, that seems like, I think, probably how most of us learn. But in reality, what we're trying to do is we're trying to make a balance. And when we look at this, like the behaviors of the way the mean works is that actually, if I was to try to find the great equalizer here, I'm trying to essentially figure out like, okay, like if we took like the game 3 where this player scored the most points, and we look at game 1 where they scored the least points, how can we like better distribute that? Well, if I took some from this high scoring game and gave it to the low scoring game, that would help us get more to what we'd call this average or this great equalizer. We're trying to essentially kind of balance the scale so that all the games, there's a consistent number of points. So as students go through this, we can see here, and you can actually see this happening before your eyes. Like we're actually moving this around and we're seeing that, wow, like in my mind, I can sort of visualize the 18 now going down and the 12 going up. And we can count those up to see that the mean is actually 15 points. For the median, I remember as a student always just like listing out the numbers, and then I'd try to pick the middle number. If there was two middle numbers, you have to like average those two out. But here it becomes like very visual and very obvious that it's like, okay, if I reorder these games, I can see that the median is going to be that middle game and it's 15 points. And actually in this case, it looks like it's probably not a bad idea to use either of those measures of central tendency. So the question could then be, how many points do you think this player is going to score at the end of a 20-game season? Right? So now they have this average. What we've done when we find this measure of central tendency, what we're doing is we're trying to find a number that makes sense to use as a rate per game. 15 points per game on average, or is the median, and we can use that number to help us make some predictions about what might happen as we move through. So this is just one small example of like a behavior in mathematics that emerges like when we're trying to find measures of central tendency that actually, our gut instinct, when we think about why we're averaging, we're trying to find a central number. And by finding a central number with the mean, we're really just trying to equal out all the groups. And that's where that division piece comes in, where you go, okay, well, if I added it all together and then divided them out, that would get me the mean right away. But the reality is that oftentimes we're not thinking about what we're doing when we engage in that procedure. So that procedure, of course, we want that to emerge to the surface as well. And hopefully some students even maybe bring it up and they say, if I just add all these numbers and then divide, that'll be great. But I would argue with a lot of students that, in the case that we just saw with these values, probably is more work, especially if you didn't have a calculator, to add up all the values and then divide by 5 rather than just redistributing the extras to some of the lower quantity games. To me, that seems like a really logical way for me to come up with a reasonable estimate. So friends, my message here for you is we need to be very careful about our questioning in our math classroom. We want to be questioning students so that we can emerge big ideas, the strategies, and the models in our math classrooms so that we can help students starting to make sense of the mathematics so that they actually understand how mathematics behaves. And then as things get more complex, they can apply that understanding of the behaviors of mathematics to other situations. So you're just having a quick peek at all the different problem-based units up on our website. Currently, we continue to develop new units each and every week. So you can head on over to makemathmoments.com/tasks. And you'll land right on this page here. And each of these tiles is actually a full unit. Now, some people ask, do I have to be a member of the Academy, of the Make Math Moments Academy, in order to access these tasks? And the answer is no. Most days, you have the problem-based lesson ready to go. Members do get more of the teacher guide moves as well as all of the downloads, but you can run these tasks straight from the web if you choose. So I would go dive in, and then even if you're using these as inspiration for how you can modify or transform some of your lessons so that you can help emerge more of the mathematical behaviors that are coming up in your curriculum with your students through questioning. That's one of our big goals here, and we're really glad that you stopped and hung out with us the entire time here. One thing you could do that would be a huge favor to us would be to hit that subscribe button and the like button. Leave us a comment. How was this video for you? Did you learn anything new? Did it give you any new takeaways? Or what could we add to the videos for next time? That would be super helpful, and we're really excited to be hanging out with you in our next video. So stick around, and we'll see you next Monday.